Usually, hardware is a physical certainty. Like you look at a circuit board, you see a metal USB port soldered right onto that green fiberglass.
Right, you can literally trace the copper lines.
Exactly. You trace those little copper lines to a black microchip, and you can point your finger at it and say, well, that right there, that is the USB controller.
Because it's tangible. I mean, when we deal with computers, we rely so heavily on that physical layer being completely distinct from the software layer.
Yeah, you write the code and the hardware just executes it.
Right, the hardware is the hardware.
But today we're diving into a system that takes that comforting physical reality and just, well, completely shatters it.
It really does.
We are looking at an environment where the hardware is entirely an illusion. Like it's a fake, generated entirely by software running so fast and so precisely that a modern computer literally cannot tell the difference.
And we aren't just looking at how that illusion is built today. We are looking at a highly technical, just meticulous manual that documents exactly what happens when that software illusion catastrophically breaks.
Yeah, so the document we're reading and explaining for you today on this deep dive is the AVR, Vusb and USBasp firmware manual.
Specifically, the mobile reader edition.
Right, dated July 18th, 2026. And this is not your standard user guide.
Not at all.
It reads like a forensic audit of a total disaster, followed by this incredibly rigorous, scientifically proven repair manual. So we're going to walk you through exactly what this document reveals about really the absolute physical limits of communication between devices.
And the context here is just so essential to grasp. The document focuses on a software framework called Vusb.
Right.
And to understand the gravity of the bugs that the manual uncovers, you first have to understand the environment Vusb actually operates in.
Okay, let's unpack this.
So imagine a bare-bones, super generic microcontroller. The manual specifically calls out a chip called the AVR ATmega88.
And just to ground this for you listening, an ATmega88 is not, a complex processor like the one in your laptop or your smartphone.
Oh, no, definitely not.
It's the kind of cheap, simple chip you might find running the timer on a microwave. Or maybe reading a really basic temperature sensor.
Exactly. I mean, it has very little memory. It runs at a relatively slow clock speed, usually something like 12 or 16 megahertz.
Which is nothing today.
Right.
Yeah.
And most importantly, it has no USB hardware built into its silicon whatsoever. It has no idea what USB even is.
It just has those generic input and output pins, right? The little metal legs sticking out of the chip.
Yeah, exactly. Legs that can either be fed a voltage or output a voltage. That's it.
But someone, at some point, realized they needed this dirt cheap chip to talk to a standard computer over USB.
And adding an external USB controller chip costs money.
And it takes up space. So instead of doing that, they decided to force this microwave timer level chip to speak USB using nothing but pure software.
Which is just wild.
That is what Vusb is, right? It's code that aggressively toggles those standard input and output pins at these exact microsecond intervals to fake the really complex electrical signals of a USB connection.
It is an astonishing piece of engineering.
Yeah.
Because to pull off that deception, you have to understand the constraints of the USB protocol.
Which are intense.
Very. The manual explicitly states this operates at low-speed USB. Now, low speed might sound sort of trivial, but in this context, it means 1.5 megabits per second.
Okay, so meaning 1.5 million individual bits of data, just ones and zeros, are flying across the wire every single second.
Right. And let's actually do the math on that because it totally frames the rest of the document.
Let's do it.
If you have 1.5 million bits per second, that means one single bit lasts for roughly 0.66 microseconds on the wire.
Less than a millionth of a second per bit.
Yep. And if your generic microcontroller is running at a clock speed of 12 megahertz, meaning its internal heartbeat ticks 12 million times a second, you just divide that 12 million by the 1.5 million bits.
Okay, and that gives you, wait.
It leaves you with exactly 8 clock cycles.
Wait, 8 clock cycles?
Exactly 8.
So the computer chip has time to execute maybe 8 basic instructions, like, I don't know, moving a tiny piece of data from one register to another before the very next bit arrives on the wire.
Precisely 8 cycles. If the software takes 9 cycles to figure out what to do with a bit, well, it misses the next one entirely.
Oh, wow.
The data gets corrupted, the computer thinks the device is broken, and it drops the connection. There is zero margin for error here.
So if the timings are this incredibly fragile, how does the connection even start? Like, how do the computer and this little fake device actually talk to each other without just stepping on each other's toes and crashing?
Well, that brings us to a foundational rule of USB that the manual relies really heavily on. The bus is entirely host-controlled.
The host being your laptop or your desktop computer.
Right. The device, our little fake VUSB microcontroller, is never allowed to speak unless it is explicitly spoken to.
Okay, I actually remember reading this in the specs. The device cannot transmit spontaneously at all. It can't just, wave its hand and say, hey, I have data for you.
Never. The host acts as an absolute dictator of the connection. So it's like a highly strict classroom where a student can literally only speak if the teacher calls their name directly.
That makes sense.
The host constantly pulls the device, sending these specific token packets that basically say, device number 4, do you have anything to send me?
And only after receiving that specific IN token is the device allowed to actually place electrical signals onto the wire.
Yes, exactly.
So the device can spend all its time preparing data, organizing its memory, getting everything ready to answer, but it has to wait in complete silence until the host points directly at it.
Right. And that electrical signal they use isn't just a simple on and off switch either.
It's more complicated than that.
Oh, yeah. The manual goes into the weeds on how the ATmega88 has to read the physical wire. It uses 2 normal pins named PD2 and PD4. And it connects those to the D+ and D- wires of the USB cable.
Right, because USB uses differential signaling, which means, for those of you listening, instead of just measuring voltage against a ground wire, it actually compares the voltage between 2 active data wires.
Exactly.
But why do they do it that way? Instead of just sending a high voltage for 1 and a low voltage for 0.
It's primarily about noise immunity. USB cables can be, relatively long.
Sure.
And they often sit right next to power cables that give off electromagnetic interference. If a spike of interference hits a single data wire, it might accidentally push a low voltage high enough to look like a 1.
Which would totally corrupt the data.
Exactly.
Yeah.
But with differential signaling, the 2 wires, D+ and D-, are always exact opposites of each other.
So if D+ goes up to, say, 3 volts, D- drops to 0 volts.
Right. So the receiver doesn't just look for 3 volts, it looks at the difference between the 2 wires. If electromagnetic noise hits the cable, it usually hits both wires equally.
Ah, I see.
So the overall voltage of both might spike up, but the difference between them remains exactly the same.
That is really clever.
The manual outlines how VUSB reads these differential states, specifically calling them the J state and the K state.
Okay, so the J state is the idle resting state, where D- is higher than D+, and the K state is just the opposite.
Yep.
But here is where the manual introduces something that genuinely confused me at first. It talks about NRZI encoding, non-return to 0 inverted.
It's a mouthful.
Yeah. If the host is sending a string of bits, it doesn't just say, J means 1 and K means 0. That would be too easy.
It would be way easier, but it wouldn't work for USB.
Yeah.
You have to remember what a USB cable actually lacks.
What's it missing?
Well, it has a wire for power, a wire for ground, and the 2 data wires we just talked about. Notice what's missing there. There is no dedicated clock wire.
Ah, and a clock wire is what usually tells the receiver when to actually read the data, right? Like a little metronome ticking alongside the data stream.
Yes, exactly. In a lot of hardware protocols, you have a separate line just ticking up and down.
Yeah.
And every time it ticks, you read the data line.
But USB doesn't have that.
Right. Since USB doesn't have that, the data wire itself has to carry both the information and the timing synchronization simultaneously.
Wow.
And that is exactly why they use NRZI encoding.
So how does NRZI actually combine the clock and the data?
By focusing on transitions rather than absolute states. In NRZI, if the host wants to transmit a 0 bit, it forces a transition. It flips the state from J to K, or from K to J.
So any flip at all basically means, hey, I am sending you a 0.
Correct. But if the host wants to transmit a 1 bit, it does nothing. It leaves the line exactly as it is, no transition at all.
Okay, wait, back up. If a 1 bit means do absolutely nothing to the voltage, what happens if the host wants to send a file that has, say, 51 bits in a row?
That's the problem.
The voltage would just sit there, completely flat, for 50 cycles. How does the receiving microcontroller know that was exactly 50 bits?
It wouldn't.
Because without a metronome, wouldn't its internal timing just drift? Like maybe it thinks it saw 49 bits or 51.
It absolutely would drift. I mean, no 2 crystal oscillators on 2 different circuit boards tick at exactly the same microsecond rate.
Right.
If the line stays flat, they lose sync very, very quickly. And that is why the USB protocol mandates a mechanism called bit stuffing.
Okay, the manual spends a lot of time on this. What is bit stuffing actually doing to the data?
It's basically a forced synchronization event. The protocol rules state that a transmitter is never ever allowed to send more than 6 1 bits in a row.
Oh, really? Never more than 6.
Right. If the data it's trying to send happens to have, 7 consecutive ones naturally, the transmitting hardware will automatically inject or stuff a fake 0 bit right after the 6th one.
And because it's a 0, that forces a voltage transition. The line flips from J to K.
Yes. And that single flip is enough for the receiver to look at the signal and say, okay, there's a hard edge. Let me realign my internal microsecond clock to that edge so I don't lose my place.
But that creates a massive headache for our little VUSB software, doesn't it?
A huge headache.
Because the host computer's hardware is injecting these fake E-zeros into the data stream to keep the clock synced. But our microcontroller doesn't have hardware to filter them out.
And that is the crux of the magic trick. The microcontroller has an interrupt pin, specifically INT0, connected to the D+ line.
Okay.
When the bus is idle, it sits in that J state. The moment a packet begins, the host forces a transition to the K state. That change in voltage acts as a physical trigger to the INT0 pin.
And the manual is incredibly strict about what happens the microsecond that trigger fires. The microcontroller has to completely abandon whatever normal application code it was running.
It is an aggressive hardware interrupt. The CPU instantly drops its current task. And we mentioned that 8 clock cycle budget per bit earlier.
Right, the 8 cycles.
Inside that tiny, tiny window, the handwritten assembly code must do a staggering amount of work.
Like what?
It has to save the current state of its internal registers to memory, so it can eventually return to what it was doing. Then it has to perfectly align its own sampling to the incoming bit cells.
Then it has to read the physical pins and decode the J and K states back into 1s and 0s using that NRZI logic.
Yes.
But then, as you just explained, it has to constantly keep count of the ones it receives, too.
Exactly.
If it sees 6 ones in a row, it has to realize the very next bit is a stuffed timing bit, completely ignore it, strip it out of the data stream, and then take the actual clean data bits, assemble them into full 8-bit bytes.
Check to see if the packet is finished.
Right. And prepare an immediate response.
All in software.
That is insane.
All calculated down to the single CPU instruction clock cycle. If a developer alters that assembly code without understanding the exact mathematical latency of every single instruction, the entire illusion collapses.
But wait, if the chip is totally paralyzed while receiving a USB packet, how does it ever find the time to actually do the thing you bought it for?
That's the million-dollar question.
Like, if I bought this chip to monitor a sensor, but it's constantly dropping everything to decode these massive USB packets, wouldn't the whole system just lock up?
You've hit on the central architectural tension of VUSB. Yes, the USB interrupt takes absolute priority and freezes the foreground application entirely for the duration of a message.
So the main code has to be written perfectly.
With extreme discipline. You cannot use long blocking delays. If your main program says, wait 10 milliseconds for the sensor to warm up, and it just halts the CPU for 10 milliseconds, well, the host computer will try to send a USB token during that time.
And because the CPU is stuck in a delay loop, it won't trigger the INT interrupt fast enough to catch the start of the packet.
Exactly. The host will get no response, it'll assume the device has been unplugged or just died, and it'll sever the connection. Your device just vanishes from the operating system.
Okay, so that really establishes the sheer fragility of this framework. It requires perfect timing, perfect memory management, and total architectural discipline. So if the timings are this fragile, what happens when developers just ignore them?
Disaster.
Right. And that brings us to the core of this manual, the forensic audit. Because this manual isn't just theory, it looks at specific firmware that users had uploaded to these generic boards files named Vusb Pro and FDXU ISP.
Yeah.
And it meticulously documents how spectacularly they failed to respect the rules we just discussed.
It really is a fascinating post-mortem of bad engineering.
Okay.
The manual breaks down confirmed defects in the uploaded code, starting with how it handled USB control transfers.
Okay.
Let's look at the write bug first, which is located in a callback function named USB function write.
So in USB terms, an OUT transaction is the computer sending data OUT to the device, right? So the computer has a file or maybe a block of configuration data, and it wants to write it to our little microcontroller.
Right. Now, because we are constrained to low-speed USB, the host cannot just dump a 64-byte payload all at once.
Because of the packet limits.
Exactly. The protocol limits low-speed packets to a maximum of 8 bytes.
So a 64-byte payload has to be chopped up into 8 separate 8-byte chunks sent one after the other.
Correct. The VUSB framework handles the electrical reception, but once it successfully receives an 8-byte chunk, it hands it up to the application's USB function write callback.
Okay.
The rules for this callback are pretty simple. You take the data, you store it, and you return a value to the framework telling it what to expect next.
Makes sense.
If you are expecting more data to complete the full 64-byte payload, you must return the number 0.
So returning 0 essentially means, I'm not done yet, keep the packets coming.
Yes, you only return the number 1 when you have received the absolute final packet, signaling to VUSB that the transaction is complete and it can formally close the connection state with the host.
Okay, but the audit discovered that the original code written for these boards completely ignored the incoming data length.
Ignored it completely.
When the computer sent the very first 8-byte packet of a 64-byte payload, the code just blindly accepted it and immediately returned the number 1.
It signaled completion prematurely.
The impact of that is staggering. I mean, the computer thinks, great, they got the whole message. The VUSB framework shuts down the reception state.
Yep.
But what happens to the remaining 56 bytes of data the computer was trying to send?
They are permanently discarded. I mean, the host might try to send them, but the device is no longer in a state to receive them properly. Or it just overwrites the initial 8 bytes over and over again.
Wow.
The manual confirms that any multi-packet write would silently truncate after the first packet. If you were trying to send complex configuration settings to the device, it would fail, but neither the host nor the device would throw an explicit error. It literally just black holed the data.
That is wild. But as destructive as throwing away incoming data is, here's where it gets really interesting. The manual points out a read bug that is significantly worse.
Oh yeah, the USB function read flaw.
Let's talk about this because this gets into actual security vulnerabilities.
So this occurs during an IN transaction, where the host asks the device to send data up to the computer. Let's say the computer issues a command requesting exactly 16 bytes of status information from the device.
Okay, so VUSB receives that request, triggers the interrupt, decodes it, and calls the USB function read function in the application, basically saying, hey, the boss wants 16 bytes, hand them over.
Right. And the callback is supposed to gather the requested information, copy it into a specific transmission buffer, and then return the number 16, telling VUSB, here are the 16 bytes you asked for, send them out.
And what did the audited code actually do?
It correctly returned the number 16. It told the framework, yes, I am ready to send 16 bytes.
Okay.
But it completely failed to actually write any new meaningful data into that transmission buffer.
Wait, what? So the VUSB framework dutifully goes to the buffer, grabs 16 bytes, and sends them across the wire to the computer.
Yep.
But what exactly is it sending if the application never put the status data in there in the first place?
It transmits whatever happened to be sitting in that memory space at the time.
Oh, no.
This is a severe issue known as a stale RAM leak. The Atmega88 uses static random access memory, or SRAM, as its working scratchpad. Variables, temporary calculations, buffers, they all live in SRAM.
And when a function finishes, it doesn't automatically go back and securely erase the scratchpad, does it?
No, not at all.
The ones and zeros just sit there until something else explicitly overwrites them.
Precisely. We call that uninitialized or stale memory. So imagine a hypothetical scenario where this generic chip had previously been used to process, say, an RFID badge swipe, or maybe handle a cryptographic handshake.
Right.
The sensitive data from that previous operation is just lingering in the SRAM.
Then the host computer asks for a mundane status update, the read bug triggers, and instead of sending the status, the device just blindly scoops up 16 bytes of that lingering stale memory and broadcasts it over the USD wire.
The manual highlights this as a profound flaw. I mean, the device was unknowingly exposing its internal raw state to the host computer.
That's terrifying.
Even without a malicious actor trying to exploit it, purely from a functional standpoint. The host is receiving garbage data when it expects a precise status code.
Yeah.
Which leads to totally unpredictable software behavior on the PC side.
Okay, so we have data being thrown into the void on writes and raw memory being leaked on reads. But the audit digs even deeper into the physics of the board itself.
It does.
There's a section on a 16 megahertz timer disaster that really illustrates how one small assumption can just cascade into total failure.
Yeah, this bug is specific to the FDX UISP firmware, which was meant to turn this AT-Mega chip into a USBasp programmer.
And a programmer is a device whose sole job is to force new firmware onto other blank microchips, right?
Exactly. And to do that, it needs to communicate with the target chip using very, very precise electrical pulses.
Okay.
The original historically correct USBasp hardware was designed around a CPU clock speed of 12 megahertz. But the manufacturers of these specific uploaded boards decided to bump the CPU crystal up to 16 megahertz, presumably just to make the board process data faster.
Which seems logical. More megahertz equals more speed.
Right.
But the audit found they changed the hardware clock without updating the firmware's internal math. Let's walk through why that is so devastating. How do embedded programmers actually track time without a real-time clock?
Well, they rely on hardware timers built into the silicon. If a developer needs to hold a pin high for exactly 320 microseconds to satisfy a memory chip's physical write requirement, they don't use a stopwatch.
Obviously not.
They configure a timer to tick at a known rate, and they simply count the ticks.
And the manual breaks down the math for timer 0. The timer doesn't run at the full speed of the CPU, does it?
No, it uses a prescaler.
Right. The code divided the CPU frequency by 64.
So let's follow the math the manual lays out. On the original 12 megahertz board, the CPU ticks 12 million times a second. Divide that by the 64 prescaler, and timer 0 ticks 187,500 times per second.
Okay, so if we divide 1 second by 187,500, we get the time for exactly 1 tick. It comes out to about 5.33 microseconds per tick.
Now, the developer needed a delay of 320 microseconds. If each tick is 5.33 microseconds, you just divide 320 by 5.33.
And the answer is exactly 60 ticks.
Right. So the developer hard-coded the number 60 into the software, basically saying count to 60, then proceed.
That works perfectly at 12 megahertz. But then someone swapped the physical crystal on the board to 16 megahertz and just flashed the exact same code onto it.
So let's run the same math at 16 megahertz. 16 million divided by the 64 prescaler equals 250,000 timer ticks per second.
Which means 1 second divided by 250,000 is exactly 4 microseconds per tick.
The tick got faster, but the audited code still had that hard-coded number 60 in it. It was still saying count to 60.
So at 16 megahertz, 60 ticks multiplied by the new 4 microsecond tick length is only 240 microseconds.
Exactly. The delay was supposed to be 320 microseconds. It was firing at 240. The timer was triggering 80 microseconds entirely too early.
Every single time it tried to pause.
Every time. And this error cascaded through the entire system architecture. The manual notes several critical failures.
Like what?
Well, a 15-unit fallback delay used for older, slower target chips was mathematically supposed to take 4.8 milliseconds. Because of the bug, it was executing in just 3.6 milliseconds.
Ouch.
A longer 30-unit wait, specifically designed to give EEPROM memory enough time to physically burn data, was supposed to be 9.6 milliseconds, but it was cutting off at 7.2.
What happens to the target chip when the programmer rushes it like that?
It causes silent corruption. Writing to flash memory isn't instantaneous,
Yeah.
You are physically forcing electrons into floating gates. It takes time.
So if it doesn't wait?
If the programmer shoves a byte of data into the chip and then immediately shoves the next byte in before the first one is finished running, the data is scrambled. The firmware was violently violating the physical timing specifications of the silicon it was trying to program.
But the manual's repair for this is elegant, honestly. They don't just hard code a new number.
No, they didn't.
They rewrote the code to derive the delay constant explicitly from an FCPU macro. So the compiler does the math at build time. 16 million divided by 200,000 ensures the constant perfectly adapts to 80 ticks, restoring the exact 320 microsecond delay, regardless of whatever crystal is on the board.
It removes human error from the equation entirely by making the compiler prove the math.
And speaking of math errors, we have to talk about the 8-bit trap.
Oh, this one is classic.
This is another bug in the audit that feels like a ticking time bomb regarding modern hardware compatibility. It has to do with how the programmer counts beta pages.
Right. So when you program an AVR microchip, you don't send the entire program at once, and you don't write it one single byte at a time either. That would be painfully slow.
So what do I do?
The architecture uses pages. You load a temporary buffer, say 64 bytes of data, and when the buffer's full, you send a single high-voltage command that commits that entire 64-byte page into the flash memory grid all at once.
So the programmer firmware receiving the data from the PC needs to know when that page buffer is full. It needs a variable to act as a counter.
Exactly.
Every time a byte arrives, the counter goes up by 1. When the counter equals the page size, it triggers the commit command.
And the audit discovered that the original developers used a standard 8-bit integer for this variable called prog page counter.
Now, to someone not steeped in computer science, an 8-bit variable sounds fine. It's a standard chunk of memory. Why does the manual flag this as a critical failure?
You have to understand the hard mathematical limit of 8 bits. In binary, 8 bits can represent numbers starting at 0 and going up to a maximum of 255. That is its absolute ceiling.
So if I'm programming an older, smaller chip that only has a 64-byte page size, the 8-bit counter is perfectly fine. It counts 1, 2, 3, hits 64, triggers the memory commit, and resets to 0 for the next page.
Even a 128-byte page works completely fine.
But the manual explicitly points out that modern chips, the very chips this programmer is often bought to support, frequently utilize 256-byte pages.
Right, so let's walk through exactly what happens in the code when it tries to fill a 256-byte page using an 8-bit counter.
Okay.
The bytes start arriving, the counter increments, it hits a 250, 254, 255. The variable is completely full. Now the 256-byte arrives, and the code tells the 8-bit variable to add one more.
But it can't go to 256. The memory physically cannot hold that number.
So it overflows. It undergoes an integer underflow. Just like a mechanical odometer in an old car hitting 99,999 miles and rolling over to all zeros, the 8-bit variable rolls over from 255 straight back to 0.
The counter never reaches the number 256.
Never. And because the logic statement in the code says, if counter equals 256, then commit memory, that trigger condition is never, ever met.
Oh, so the programmer just keeps blindly accepting data from the PC, silently overwriting its own internal buffer over and over.
Yeah.
And it never actually burns anything to the target chip's flash memory.
Yep.
It's just an infinite loop of failure caused by choosing a variable type that was exactly 1 bit too small.
The repair documented here is almost deceptively simple, but it requires that forensic level of auditing to even find it. They simply changed the variable declaration from an 8-bit AINT to a 16-bit innate 16.
And a 16-bit integer can hold numbers up to 65,535.
Which trivially handles a 256-byte page, ensuring the logic trigger finally fires.
It's a textbook example of how legacy assumptions like assuming pages will always be small just break down as hardware evolves.
Exactly.
So we've walked through the audit. The old firmware was discarding write data, leaking raw SRAM on reads, firing its timers 80 microseconds too early, and was mathematically incapable of counting high enough to support modern chips.
The system is fundamentally broken.
This brings us to the core of the manual, the philosophy of the repair. How do you approach fixing a code base with this much rot?
Well, you start with a very strict policy of containment. The manual details a profound philosophical choice. The repair team decided they were absolutely not going to try and manually patch the lowest level USB assembly code.
Right. The manual notes that the uploaded broken firmware was using a customized, locally edited version of the core VUSB files, which the original developers had renamed to Vusb and Pro.
Yeah, they had gone into the assembly files and tinkered with the instruction flow.
Which, given what we discussed earlier about that strict 8-clock cycle budget, is incredibly dangerous.
Oh, it's reckless. High-level C code is relatively forgiving, right? The compiler handles the memory placement, but assembly code is raw machine instructions.
You're touching the metal.
Literally.
Yeah.
If you add a single instruction to check a custom flag, or if you accidentally alter how the CPU allocates a register during that INT0 interrupt, you alter the execution time by 1 or 2 microseconds.
And as we established, if you are off by a microsecond, the NRZI synchronization fails, the stuffed bits aren't removed in time, and the entire USB packet is corrupted. The physical illusion collapses.
So the repair team made a highly disciplined engineering decision. They deleted the entire Vusb Pro customized core. They completely removed it from the project.
Just threw it out.
In its place, they brought in the original, mathematically verified, factory standard VUSB framework files from the official December 6, 2012 release. Byte for byte, identical.
Because they realized that the low-level electrical timing was not the problem. The core framework was actually fine.
Exactly.
The catastrophic bugs were entirely in how the application layer was interacting with that core.
It establishes a really clear boundary.
Right.
The low-level timing belongs to the 2012 core. Improvements, configuration, and state tracking belong strictly in the application callbacks.
That makes total sense.
They instituted a new core policy that mandates the USBDOV directory must never be altered locally. This centralizes identity checks and guarantees the electrical foundation is just completely stable.
And once that foundation was restored, they introduced strict new software policies to prevent the application layer from crashing the system again. The manual details the program policy. Can you walk us through how memory allocation works on these chips and why this policy matters so much?
It comes back to the severe resource constraints of the 8MEGA88. We talk about SRAM, the working scratchpad memory.
Right.
SRAM is highly limited, often just 1 or 2 kilobytes on these chips. But the chip also has flash memory. Flash is where the actual compiled program code is permanently stored, doesn't erase when the power goes off, and there's generally much more of it available than SRAM.
And in the C programming language for AVR chips, there is a specific macro called progmem that allows a developer to tell the compiler, hey, don't put this data in the tiny SRAM scratchpad, store it permanently in the flash memory instead.
Exactly. Now, to be recognized by a computer, a USB device has to provide descriptors.
What are those?
These are data structures that basically announce, I am a USB device, my vendor ID is this, my product ID is that, and here's the maximum size of my data packets.
Those descriptors don't change, do they? Like the vendor ID is static.
Right. So the new policy mandates that all of these static descriptor tables must be forced into flash memory using progmem.
Ah, I see.
The old code was casually letting these static arrays load into the precious SRAM at startup, wasting vital scratchpad space that was desperately needed for handling the actual USB payloads.
The manual also notes a dangerous habit in the old code regarding memory pointers. When it needed to send a reply to the host, it would point the VUSB transmission engine in a local automatic variable. What does that mean, and why is it so bad?
A local automatic variable is a temporary piece of data created entirely inside a specific function. As soon as that function finishes running, the C compiler automatically destroys that variable and frees up the SRAM for something else.
So if the application says, hey, VUSB, the data you need to send is right here in this temporary variable, and then the function ends,
The variable ceases to exist. The memory address is instantly reallocated to whatever the CPU decides to do next.
oh boy.
But the USB transmission might take several microseconds to actually clock out onto the wire. By the time that the USB framework tries to read that memory address, the original data is gone, overwritten by new random CPU operations.
So the framework just ends up transmitting garbage.
Which explains the totally unpredictable behavior users were seeing. To fix this, the new policy dictates that any runtime replies must be stored in statically allocated, globally stable RAM buffers.
Memory of the compiler is strictly forbidden from reallocating until the transmission is officially closed.
Yes, it is a fundamental cleanup of memory lifecycle management. But the most profound architectural shift in the manual is what they call the blocking policy. This completely changes how the device thinks about time.
The manual is incredibly blunt here. It says, in bold text, do not call delames inside an active callback. Do not spin until EEPROM, ADC, SPI, display, or serial work completes.
This goes back to our earlier discussion about the central tension of a USB. Remember, the host is a dictator. It demands an immediate response.
Right.
If the microcontroller gets a USB command that says, go write this data to the slow EEPROM memory, and the microcontroller decides to just sit there in a while loop waiting for the slow memory to finish physically burning the data.
The CPU is stuck in the loop. It isn't listening to the USB wire.
And while the CPU's back is turned, the host computer sends the next token. The device misses it. The connection crashes. Linear blocking programming, where you execute step A, pause, and wait for it to finish, then execute step B, is fundamentally incompatible with software USB.
So how do you write code if you aren't allowed to wait for things to finish?
You have to redesign the entire application as a non-blocking state machine.
I hear the term state machine a lot in embedded systems. Can you break down what that actually looks like in practice?
Okay, think of a chef in a restaurant kitchen. A linear programmer is a chef who takes an order for a steak, puts it on the grill, and then stands there staring at the steak for 15 minutes until it's done, completely ignoring the 10 new tickets printing out.
That is not a very efficient kitchen.
Not at all. A state machine is a short order cook. They put the steak on the grill, that's state cooking.
Yeah.
Then they immediately turn around, check the ticket printer, drop fries in the fryer state, frying prep a salad, and then glance back at the steak to see if it needs flipping.
I love this analogy.
They are constantly cycling through all open tasks, doing tiny instantaneous checks, and never ever stopping to wait for a slow physical process.
So in the context of this VUSB chip, the main loop of the program is the cook constantly checking the tickets. It repeatedly, aggressively calls a core function named USBPoll.
Yes, USBPoll is the function that listens to the wire and handles the USB traffic. The new blocking policy mandates that any heavy lifting the application needs to do, reading a sensor, writing to flash memory, must be broken down into incredibly short, microsecond-level steps that execute between calls to USB pole.
So you do one tiny step. You immediately call USB pole to service the USB connection. You do the next tiny step. You call USB pole again.
Exactly. You interleave the slow hardware tasks with the constant USB maintenance.
It prevents the CPU from ever turning its back on the host computer for too long.
Precisely.
And the manual doesn't just mandate this philosophy, it proves it. The next major section provides 5 complete progressive software examples. It starts from 0 and builds up to a highly complex application, proving that these new policies result in rock-solid stability. Let's walk through how these examples logically build the case.
The progression is very deliberate, acting as a tutorial for the repaired framework. Example 1 is the absolute minimum viable device. It has no application logic, it doesn't read sensors or write memory.
It's literally just a pulse check.
Basically, it proves that the restored 2012 core can wake up, assert the physical pull-up resistor on the D- line, which is the electrical signal that tells the host computer, hey, a low-speed device just plugged in, and then deterministically enumerate with the operating system.
Enumeration being the complex handshake, where the computer asks for all those program descriptors we talked about, figures out what drivers to load, and formally establishes the connection.
Right. Example 1 proves the basic electrical and state foundation is secure. Then, example 2 introduces memory safety. It builds a device that accepts data from the host and echoes it back.
Okay, so this directly targets and proves the death of the terrifying data discard and stale RAM leak bugs.
Exactly.
How does it safely echo the data without leaking?
It introduces a 64-byte bounded buffer allocated in stable RAM. When a write request arrives from the host, the framework's setup function registers exactly how many total bytes the host intends to send, and it initializes a countdown variable.
So it knows exactly what is coming.
Yes. Then, as those tiny 8-byte packets arrive one by one, the new USB function write callback doesn't just blindly return 1 like the old code. It strictly validates the incoming chunk against the buffer's mathematical bounds so it doesn't overflow memory.
Brilliant.
It copies the data into the stable buffer. It decrements the countdown variable.
And it only returns 1 when that countdown hits exactly 0, meaning it has safely consumed every single byte the host intended to send. The data discard bug is mathematically eliminated.
And for reading, when the host asks for the data back, the Gopher function read utilizes a persistent transfer state variable. It knows exactly where it left off, and it carefully slices the stable buffer back into 8-byte chunks, sending them up without ever touching uninitialized SRAM.
The stale leak is closed.
Yep.
Example 3 moves to physical hardware interaction. It configures a pin, PB0, as an input to read a button, and another pin, PD7, as an output to toggle an LED. This simply proves that the continuous USB pull state machine doesn't get interrupted or corrupted when the chip is manipulating its physical environment.
But example 4 is where the state machine architecture is truly pushed to its limits. The manual highlights this as the ultimate proof of the non-blocking policy. It implements block read and write for the internal EEPROM.
Now, EEPROM stands for Electrically Erasable Programmable Read-Only Memory. It's built into the chip to store settings that need to survive when the power is turned off. But physically, it's very slow to write to.
Exceptionally slow. While the CPU operates in microseconds, burning a byte into EEPROM takes milliseconds. It is a massive physical bottleneck.
Wow.
If the USB host sends 32 bytes of configuration data, and the device tries to burn them to EEPROM synchronously, meaning it waits for byte 1 to finish before moving to byte 2, the whole process will take tens of milliseconds.
And the VUSB connection will instantly time out, dropping the device from the operating system. So how does example 4 solve this using the chef analogy we discussed?
It uses a technique called staged writes. When the 32-byte payload arrives from the USB host, the microcontroller does not immediately talk to the EEPROM hardware. Instead, it accepts the entire payload at full USB speed and dumps it into a fast temporary RAM buffer.
The short order cook takes the ticket and slaps it on the rail.
Exactly. The USB control transfer is immediately flagged as complete. The host computer is perfectly happy. It thinks the configuration was saved instantly.
But it hasn't been saved yet.
No. The firmware returns to its main loop, constantly calling as bpoll. In the background, a separate task function, the cook glances at the RAM buffer. It sees pending bytes. It checks a hardware flag on the EEPROM circuit to see if it is currently busy. If the EEPROM is idle, the task launches the physical write command for just one single byte.
And then it immediately turns its back on the EEPROM and goes right back to calling us bpoll.
Yes, the physical EEPROM hardware is doing the slow burning of that byte completely independent of the CPU. The CPU is totally free to maintain the USB connection.
That is so smart.
A few milliseconds later, the background task checks again. If the EEPROM is finished, it feeds it the next byte from the RAM buffer. It interleaves the slow physical hardware writes perfectly with the high-speed USB polling requirements.
The manual also notes a brilliant optimization here. Before it writes a byte to EEPROM, it checks if the value in the EEPROM is already identical to the new data.
Right.
If it is, it skips the RAID entirely. That not only saves milliseconds of time, but it reduces physical wear and tear on the EEPROM cells, which have a limited number of write cycles before they physically degrade.
It is an incredibly sophisticated non-blocking architecture.
This leads us to example 5, which genuinely blew my mind when I read it. Example 5 is about speed and integrity. If you want to stress test this repaired VUSB pipeline to see how much data it can handle without dropping a packet, you normally need to send massive blocks of data back and forth.
Right. Usually you would send a huge 254-byte payload, store it in memory, and then send it back to verify no bits were dropped.
But our little ATmega88 doesn't have 254 bytes of free RAM to spare just for a test buffer. So how do they prove the system can handle massive throughput without running out of memory?
They replace memory with pure mathematics. Example 5 doesn't store the payload at all. It uses a mathematical formula, often something like a linear congruential generator, to calculate what the data should be on the fly.
So the data is entirely deterministic.
Yes. The host computer and the device both know the mathematical formula. The host initiates a massive transfer and sends a starting seed number. As the host strings the resulting data sequence across the USB wire, the receiving microcontroller doesn't save it.
It just processes it.
It simply runs the math formula for every incoming byte and compares the physical byte received against the calculated byte.
If the byte arriving on the wire matches the math, it throws the byte away and waits for the next one. If it doesn't match, it flags a corruption error.
And for transmitting back to the host, it does the exact reverse. It just runs the formula and spits the calculated bytes onto the wire as fast as the host requests them.
That is genius.
This brilliant approach totally decouples the VUSB performance test from any RAM limitations. It allows the host to hammer the device with maximum length transfers, proving the framework can saturate the low-speed USB wire without a single microsecond of latency causing a crash.
It's an airtight proof. So the core is audited, the memory philosophy is fixed, the state machine is implemented, and the math proves it holds under pressure. Now, the manual transitions into applying all of this to a highly specific real-world tool, the USBasp programmer firmware.
The USBasp is an open-source hardware design used by thousands of engineers to flash target chips. The overarching goal of the manual here is rigorous compatibility. The repaired firmware must perfectly understand the commands sent by standard host software. Specifically, a really popular program called AVRDUDE, but it has to process those commands using the vastly superior, newly repaired internal architecture.
And looking under the hood of how they fix the programmer code brings us to a fascinating discussion about Clang assembly cleanup.
Oh, yes.
Clang is a compiler, the software that translates human-readable C code into the raw machine instructions the microcontroller actually executes.
And embedded engineers are constantly in a battle with the compiler to make sure it generates the fastest, most efficient machine code possible. The manual's audit found a massive architectural bottleneck in the old firmware regarding how it processed ISP commands.
ISP stands for in-system programming. When the USBasp wants to talk to a blank target chip, it uses an ISP serial connection.
Right. ISP relies on sending 4-byte commands. The old firmware had a really complex internal decision tree. Sometimes it needed to send those 4 bytes using the chip's fast, dedicated hardware SPI pins. Other times, if it was talking to an older target chip, it had to manually toggle standard pins in software to send the bytes slowly.
So the code had to constantly decide, am I using the fast hardware function or the slow software function?
To manage this, the original developers used function pointers. In the C language, a function pointer is a variable that stores the memory address of a function. The logic essentially said, go look at this variable, find the address written inside it, and jump to that address to execute the code.
Why does the manual highlight this as a problem? I mean, function pointers are used everywhere in high-level programming.
On a desktop processor, they're totally fine. But on an 8-bit microcontroller with a very limited execution pipeline, an indirect jump, which translates to an I call machine instruction, is tremendously expensive.
Let me make sure I understand the difference here. A direct jump is the compiler saying, go directly to line 50. The CPU knows exactly where it's going next, so it can prepare.
Right.
An indirect jump, the I call, is the compiler saying, go open the drawer, look at the piece of paper inside, and jump to the line number written on it.
Exactly. And because the CPU doesn't know what's on the paper until it actually opens the drawer at runtime, it can't optimize the execution path. It has to stall its internal pipeline.
That sounds slow.
The audit found that the old firmware was executing 4 separate, slow, indirect ICL jumps for every single programming command.
And if you are flashing a target chip with 30,000 bytes of code, you are forcing the poor processor to execute tens of thousands of these stalled indirect jumps just to figure out which pin wiggling function to use. The overhead is massive.
So the repair team ripped the entire function pointer architecture out. They replaced it with direct, hard-coded conditional paths based on a single static mode flag. The manual specifically documents that a static analysis of the compiled client output proves the ICL instruction has been entirely eradicated from the firmware.
But the compiler audit found something even more dangerous than slow jumps. It found what the manual calls strict aliasing and pointer alignment issues. This gets incredibly technical, but it's vital to understanding how code can just suddenly break.
This is a classic trap in C programming. The old code was receiving 4-byte ISP instructions from the USB connection as an array of 4 separate 8-bit bytes, but the code needed to process them as a single 32-bit integer.
So the developer just told the compiler, hey, look at these 4 separate 1-byte boxes in memory and just pretend they're actually one large 4-byte box. That's a pointer cast, right?
Yes, they cast an 8-bit pointer to a 32-bit pointer. But this violates a fundamental rule of modern C compilers called strict aliasing.
Which means
the compiler's optimizer assumes that a pointer to an 8-bit variable and a pointer to a 32-bit variable will never point to the exact same physical memory address.
why does the compiler assume that?
Because if it assumes they are separate, it can violently optimize the code, caching values in registers instead of constantly checking RAM.
Ah, okay.
But if you break the rule and cast a pointer anyway, the optimizer looks at the code and says, well, the rules say this is mathematically impossible, so this code must be dead or invalid. And it can literally delete the code or rearrange it in a way that causes completely undefined behavior.
And there's a hardware alignment issue too, right?
Yes, the endianness and alignment trap. A 32-bit integer physically requires 4 bytes of memory. Many microcontrollers demand that 32-bit integers be stored at memory addresses that are evenly divisible by 4.
Okay, so they have to line up perfectly.
Right. If your array of 8-bit bytes just happens to start at an odd memory address and you try to read it as a 32-bit integer, the CPU hardware will crash because the memory is misaligned. Furthermore, the old code blindly assumed the bytes were stored in little endian format, meaning the least significant byte is stored first, which isn't always true across different systems.
It was basically a house of cards relying entirely on luck and old, unoptimized compiler behavior. How did the manual repair this?
By respecting the math, instead of trying to trick the compiler with unsafe pointers, the new firmware explicitly constructs the 32-bit integer mathematically.
How so?
It takes byte 1, shifts it left by 24 bits, takes byte 2, shifts it left by 16 bits, and logically ORs them together.
So it manually builds the integer from scratch, completely bypassing the strict aliasing rules and guaranteeing perfect alignment and endianness, regardless of how aggressively the compiler tries to optimize the code.
It's bulletproof code. And the manual applies the same rigor to the protocol logic, specifically addressing a stale state read bug within the program of commands.
This sounds similar to the stale RAM leak, but it's a protocol state issue. What was happening during read operations?
When the host software, ADRDUDE, wants to read the flash memory off a target chip to verify it was written correctly, it sends a setup command saying, I am going to read exactly X bytes. The device prepares to send them.
And as we know, it has to send them in 8-byte packets.
The old firmware had a logical flaw in how it determined the read was finished. It looked at the size of the packets it was sending. The logic essentially said, if I ever send a packet that is less than 8 bytes long, that means I've run out of data, so the transfer is complete, close the state.
Okay, wait. Let's trace that logic. What happens if the host software requested exactly 16 bytes?
So the firmware prepares 16 bytes. It sends the first packet. It is exactly 8 bytes long. Is it less than 8? No. So it keeps the state open.
It sends the second packet. It is exactly 8 bytes long. Is it less than 8? No.
And that's the end of the data. The host received its 16 bytes and is satisfied. But the device firmware never saw a packet less than 8 bytes long.
So the device never logically closed the transfer.
Exactly. It left the internal read state locked open. This is a stale state. The device just sits there, indefinitely expecting the host to ask for more read data.
But the host is done, the host moves on and sends a completely different command, like erase the chip.
And the programmer, stuck in its stale read state, misinterprets the erase command, causing a protocol crash. The host throws an error, and the user has to physically unplug the programmer to reset it.
The repair fixes this by abandoning the packet size logic entirely. The new firmware maintains a strict, mathematically precise countdown of remaining bytes. It decrements the counter exactly.
Yep.
And when that counter hits absolute zero, it forces a persistent return to the idle state, unequivocally closing the transfer regardless of what size the final packet was.
It completely eliminates ambiguity. And all of these optimizations, the memory policies, the Clang assembly, direct paths, the state cleanup, they all serve one ultimate purpose for the end user: speed.
Which brings us to the final major exploration in the manual, Section 6, the quest for 10 kilobytes. For anyone using a programmer, flashing a chip is dead time. You just sit there watching a progress bar.
It's agonizing.
The manual notes that the baseline speed users were experiencing with the old, broken firmware was a sluggish 2.6 kilobytes per second.
So the defining question of the manual's final chapter is, after stripping the firmware down to the studs and rebuilding it with perfect efficiency, can they hit the psychologically satisfying barrier of 10 kilobytes per second?
To answer that, the author doesn't just run a speed test and print a number. They do something much more valuable. They mathematically deconstruct time itself.
I love this section.
They ask, where exactly does the time go during a single flash write operation? Because it is not a single smooth pipe. It is a series of distinct physical bottlenecks. Let's break down the timing model the manual presents.
So the data's journey starts on the PC. First, there is host scheduling overhead. AVRDUDE, running on Windows or Linux, has to ask the operating system to access the USB port.
Yeah.
The OS groups the firmware data into blocks, usually 200 bytes at a time.
Then we hit the USB connection limit we've been discussing all day. Low-speed USB, 1.5 megabits.
Right. To push a 200-byte block across low-speed USB, it must be chopped into 25 individual 8-byte packets. Each one of those packets requires a setup stage, an interrupt trigger on our microcontroller, the decoding assembly sequence, a data stage, an acknowledgement, and a status stage.
So the overhead of the USB protocol itself is massive.
But the manual runs the math to see if the USB wire is the limiting factor. Ignoring everything else, just looking at the theoretical maximum throughput of the low-speed USB protocol handling 200-byte blocks. What is the ceiling?
The formula in the manual calculates the optimistic USB wire bound to be roughly 78.4 kilobytes per second.
78.4.
So even at low speed, the USB connection can easily handle 7 times the 10 kilobytes goal. The USB wire is not the bottleneck here.
No, the bottleneck is what happens after the data gets to the programmer.
Correct. Now the programmer has to send the data to the blank target chip over the ISP connection. And the ISP protocol is brutally inefficient for bulk data. The manual highlights an inescapable ratio. 4 ISP bytes are required to physically commit 1 single byte of payload to the flash memory.
Why does it take 4 bytes just to write one?
Because you aren't just sending data, you are sending commands over a serial line. You have to send a byte to, say, enable programming mode. Then you send a byte for the high address of the memory grid. Then a byte for the low address. And finally, the 4th byte is the actual piece of payload data you want to save.
Oh, that makes sense.
And data is transmitted over this serial line using a clock signal called SCK, the serial clock. The default standard speed for the USBasp SCK is 500 kilohertz.
500,000 clock ticks per second. And transmitting 1 byte takes 8 ticks. So 4 bytes of ISP overhead times 8 ticks per byte equals 32 SCK clock cycles required for every 1 byte of actual usable payload.
So if we divide our 500,000 tick clock by 32 ticks per payload byte, what is the absolute mathematical ceiling for transferring data across the serial wire?
500,000 divided by 32 gives an absolute maximum serial speed of 15,625 bytes per second, or 15.6 kilobytes per second.
Okay, 15.6. That's closer to our 10 kilobytes goal, but it's still safely above it, so we should be able to hit 10.
Only if writing memory was instantaneous. But we had to factor in the final, most brutal bottleneck of all, target page commit time.
But the burn time.
Remember how flash memory works?
Yeah.
You fill the temporary page buffer, let's say a 128-byte page, but then you have to send the command to physically burn that data into the silicon.
And the manual provides an illustrative model using a 4.5 millisecond physical commit time. During those 4.5 milliseconds, the entire data pipeline is backed up. The serial line is silent. The USB host is waiting. Everything halts to let the physical electrons settle into the floating gates.
Now we have all the variables for the manual's final mathematical model. We have a 128-byte page, we have a serial transfer speed limited to 15.6 kilohertz, and we have a 4.5 millisecond hard stall every single time a page finishes.
When you plug all of that into the formula, what does the physics of the system dictate as the maximum possible speed?
Factoring in the serial transfer time plus the page commit stalls, the absolute theoretical maximum throughput drops to 10.085 kilobytes per second.
10.085. It's barely over the line.
And critically, that 10.085 number assumes a perfect universe. It excludes all the USB packet overhead, it excludes the microseconds the firmware takes to execute, and it excludes the time AVR-DUDE takes to prepare the next block on the PC.
It's just the pure physical limits of the serial line and the flash memory.
Exactly. So the manual concludes that if your serial clock is set to 500 kilohertz, reaching a real-world, end-to-end speed of 10 kilobars is mathematically impossible. The physics simply forbid it.
The 10 kilobase dream is dead.
At 500 kilohertz, yes. But the manual doesn't just accept defeat. The authors analyzed the physics and realized there was exactly one variable they could change.
They couldn't change the 4.5 millisecond flash commit time that's hardwired into the target chip.
Right. And they couldn't change the USB protocol overhead.
But they could change the serial clock speed, the SCK.
The manual introduces a new software build option, explicitly mapping the IUDO clock policy to run at 2 megahertz instead of the default 500 kilohertz.
They quadrupled the speed of the serial communication.
Let's run the math again with a 2 megahertz clock. 2 million ticks per second divided by the 32 ticks required per payload byte. The pure serial ceiling jumps from 15.6 kilohertz to a massive 62.5 kilohertz.
And when you feed that much faster transfer rate into the page rate model alongside the inescapable 4.5 millisecond commit stall,
the new theoretical limit for a 128-byte page skyrockets to 19.548 kilobytes per second.
Boom! 19.5. By quadrupling the serial clock, the physical ceiling is raised so high that even after you subtract the USB protocol delays, the firmware execution time, and the host computer scheduling, hitting a real-world 10 kilobits is finally mathematically plausible.
It is plausible, but the manual immediately follows this mathematical victory with a severe hardware warning.
Naturally.
Just because the programmer firmware is now efficient enough to output a perfectly stable 2 megahertz clock signal does not mean the real world will accept it.
The programmer is pushing the signal, but there is a target chip on the receiving end. What if the target chip is running on its own internal, uncalibrated 1 megahertz oscillator? It won't be able to physically detect a 2 megahertz signal, it's just too fast.
Or consider the physical wires connecting the programmer to the target board. If you're using cheap, unshielded jumper wires that are 6 inches long, pushing a 2 megahertz square wave down those wires creates electromagnetic reflection and signal degradation.
The square wave turns into a mushy curve.
Exactly, and the target chip reads garbage.
So the math proves it is possible, but the physical environment dictates whether it is survivable.
This is where the manual elevates itself from a simple user guide to a really scientific document. It contains a strict caveat. Absolutely no speed result is claimed as measured or guaranteed in the document itself.
Wow.
All the numbers we just derived are static, modeled calculations. The manual explicitly states that the user must verify their own physical hardware limits using the scientific method.
It provides a rigorous 7-step laboratory procedure for benchmarking. You don't just flip the 2 megahertz switch and hope for the best.
Step 1. Benchmark your original broken firmware to establish a true baseline. Step 2. Flash the repaired firmware, but keep the clock exactly the same at 500 kilohertz.
So this isolates the variable. Any speed increase you see here is purely the result of the Clang assembly optimizations and the non-blocking state machine architecture we discussed earlier.
You prove the code is better before you touch the hardware limits.
Exactly. Then you manually sweep the clock speeds using terminal commands to find exactly where your specific target chip and jumper wires fail. You find the physical breaking point of your setup.
Only then, if your hardware survives the manual tests, do you compile the permanent 2 megahertz fast target build.
And it demands scientific reporting. If you post your speed results online, the manual dictates you must include the raw trial times, the median times, the specific target chip model, the exact page size, the AVR-DUDE version, and whether erase times were factored in.
It demands reproducible science.
It is the ultimate expression of treating embedded firmware engineering as a hard discipline, bounded by the inescapable realities of physics.
It really is an incredible journey. I mean, we started by looking at the USB, an audacious piece of software that tricks a computer into thinking a cheap microwave timer chip is a dedicated USB hardware device.
And then we followed the forensic audit as it exposed the terrifying reality of bad code. Multi-packet data silently thrown into the void, sensitive uninitialized SRAM leaking onto the wire, 16 megahertz timers firing wildly out of sync, and 8-bit page counters mathematically trapped in an infinite loop.
We saw how the authors responded not with quick patches, but with profound architectural discipline. They restored the mathematical certainty of the 2012 core. They enforced strict memory hygiene with the program policy.
And they fundamentally reimagined the flow of time by instituting a non-blocking state machine, proving it with beautifully structured interleaved EEPROM writes and deterministic mathematical speed tests.
And then they aimed that perfectly optimized architecture at the USBasp programmer. They eradicated the ICO compiler bottlenecks, they built a mathematically impenetrable defense against strict aliasing crashes, and they permanently closed the stale read state.
And finally, they deconstructed time itself, proving mathematically that while 10 kilohertz is forbidden by the physics of a 500 kilohertz clock, it can be conquered by carefully raising the serial speed, provided the physical wires can actually handle the truth.
It is a masterclass in the invisible mechanics that power our digital world. We spend so much time marveling at gigabyte per second transfers, but digging into the microsecond latency of a 1.5 megabit connection teaches you the fundamental rules of state, memory, and synchronization.
It really does.
It proves that underneath every high-level programming language, there is a physical clock ticking relentlessly, and if your code misses a tick, the illusion shatters.
And that leaves me with a final thought for you to ponder. We just spent an hour dissecting how clever engineers wrote software to perfectly mimic a physical hardware USB port. They faked reality so well that the operating system couldn't tell the difference. If they could generate a physical hardware illusion that convincingly back in 2012, how much of the technology you interact with today is actually real? When you press a button on a touchscreen, or when your smart car senses a lane departure, or when your phone reports a physical location, how many of those hardware sensors are actually just sophisticated software illusions running on a generic chip, desperately counting microsecond ticks to keep the lie alive? And more importantly, what happens to your life when the code inevitably drops a bit and the illusion breaks?
It definitely changes how you look at the devices around you.
It really does. You look at that metal USB port and you realize the physical boundaries are just a suggestion. The solid lines between hardware and software don't exist. It's all just math running in the dark, hoping to catch the next signal before it's gone forever.